A very good morning. Welcome to the session on cryptography, network security, and cyber law. Today we will continue our discussion on Module 3. This is our 11th session on security at transport layer. So, in this session, we will be discussing on the key design ideas in SSL handshake protocol, and also we will see the issues involved in SSL record layer protocol and what we mean by open SSL. At the end of the session, you will be able to elaborate on the key design ideas of designing the key, and also you will be able to describe the SSL record layer protocol, and you will also be able to explain the concept of open SSL and the APIs that are involved in it. Now let's start with our discussion on SSL handshake. In the previous session we had seen various steps involved in SSL handshake. There are 4 steps that were involved in SSL handshake. The first step dealt with negotiating of the cipher suite for the new session that was about to be negotiated or about to be begun. And the second step was the server was sending a certificate from its end to the client, so that the client is able to use the public key of the server. And the third step was generating and deriving various key parameters, and also we have seen the keys that were generated, that is pre-master key, master key, and also the derived keys. 6 derived keys we have seen. And the last step, that is the step 4, wherein 4 messages were exchanged between the client and the server, 2 from the client and 2 from the server. We have seen that the client is trying to perform an integrity check by calculating or computing a keyed hash over all the messages that were sent from the that were exchanged between the client and the server. And and also the client was able to verify the authenticity of the server. Now, having understood these 4 steps in the SSL handshake protocol, we have certain other parameters or other issues to be discussed. So some of the issues that we will be discussing in this session is the key design ideas, and in which we will see the key exchange methods that are adopted in order to exchange the keys securely between the client and the server. And also we will see how server authentication is performed in the 4th step, and also we will discuss on the session, on the difference between the session and the connections. So moving further, okay. Now in the step 2 of SSL handshake protocol, we have seen that server dispatches its certificate to the client. Now once the client receives this certificate, what it does is it extracts the public key from the certificate, and then it uses this public key to encrypt the pre-master secret. Now let's see this in a better way. Now we have server and a client. The server sends the server certificate to the client. The client, upon receiving this certificate, extracts the public key from this certificate. Now once the public key of the server is extracted from the certificate received from the server, the client then uses this server public key in order to perform encryption of the pre-master secret. Now the question is, how do server and client realize on the pre-master secret? Now before that we will see what if the server certificate is signature only. Now, if the server certificate is signature only, which is sent by the server to the client, it means that the client and the server can use this certificate exclusively only for signature generation and verification. It cannot use this pair of keys for encryption. Now, in this case, if the signature is only, if it is a signature only certificate, in that case, the secure socket layer performs or permits the server to create a temporary public private key pair. Now, once this public private key pair are created temporarily by the server then signs the public key along with the modulus, which is used to generate the key pair. And these public key and the modulus are signed with the server's private key. They are signed with server's private key. So what is the server doing? The server is first generating a temporary public private key pair. Now this temporary public private key pair, out of that the public key along with the modulus value are signed by the server's private key. Now once this is signed, the public key along with the certificate, the signed public key along with the certificate is sent to the client. Now what does the client do? The client receives this certificate along with the signed public key. Now first it verifies the signature on the public key. So this part will be verified, which is sent from the server. And then it uses this and it uses it to encrypt the pre-master secret. Now we have seen that if the certificate is signature only certificate, in that case how SSL behaves. It creates a temporary public private key pair and then establishes a communication between the server and the client. Moving further, now what are the various key exchange methods available? Now the various key exchange methods available are RSA and Diffie-Hellman. Either one of them can be used in order to exchange the pre-master secret. Now let us see, there are two ways in which SSL can exchange the pre-master secret. One we call it as fixed Diffie-Hellman and the other one we call it as ephemeral Diffie-Hellman key exchange. Now let's see what happens in the fixed Diffie-Hellman key exchange. Now the fixed, there are, as we are aware, there is a client and a server. These are the two communicating parties who want to communicate with each other and establish a new session. In order to establish a new session, the server, now we are completely discussing about what happens in step 2 and how key is exchanged. Now server has a certificate with Diffie-Hellman key parameters. Now what are those Diffie-Hellman key parameters which server certificate has? The prime number P, the generator G and also the public key of the server. Now G raised to A mod P is public key of the server and where G is the generator, A is the private key of server and P is the prime number. Now all of these three are present in the certificate and this certificate from the server is sent to the client. Now upon receiving this certificate, the client, first what it does is it will retrieve the public key from the certificate. Once it retrieves the public key from the certificate which is sent by the server, it also takes the other parameters of Diffie-Hellman required for realizing the Diffie-Hellman keys. Now now the client chooses random number B. Now this random number B acts as private key of the client. And then having chosen the private key of the client further proceeds to compute its public key. The public key can be computed using G raised to B mod P. Now once this public key is computed at the client, now this client will send the public key to server. Now over here we can see the fourth transaction wherein the client is sending the public key to the server. Now once the server receives the public key of the client, it can proceed further with the computation of pre-master secret. Now for the computation of the pre-master secret, as we already know in Diffie-Hellman, it uses the public key of the client, that is G raised to B mod P, and to that raised to A mod P. G is generator, B is this whole set is the private is the public key of the client raised to the private key of server mod P. P is the prime number. Similarly, on the other end, client also computes a pre-master secret. Now how does the client do this? It uses the same procedure as that used by the server. It takes the public key of the server and then uses its own private key to compute the, this has to be G raised to A mod P, which is received from the server. This is the public key received from the server, raised to B mod P. Okay, you can correct it yourself. Now these two will always help client and server realize same keys. Now this key we call it as pre-master secret. Now the question is, why is this pre-master secret called as, or this entire procedure called as fixed Diffie-Hellman key exchange? Because there are fixed parameters which are present in the certificate. These are the fixed Diffie-Hellman parameters which are present in the certificate, and every time it will help the client and the server realize same keys. Now let's see what we mean by ephemeral Diffie-Hellman key exchange. In the ephemeral refers to short-lived. Now over here, let us see what happens. The certificate does not contain the Diffie-Hellman key parameters, and the certificate is signature only certificate, and it does not have any Diffie-Hellman key parameters. So the server selects the Diffie-Hellman parameters, prime number P and generator G, and then it selects a private key A and computes the public key G raised to A mod P. Now after performing all this, the server signs over prime number, generator and the public key of server. Now once these steps of selecting and signing are performed, the server then sends the message to client. Now this message that is sent by the server to the client contains the signed parameters, the public key of the server and the signatures. Now the client on the other end receives this information from the server, and then it proceeds with the calculation of pre-master or computation of the pre-master secret as discussed in the previous slide. Now why is this key exchange method called as ephemeral? Since the Diffie-Hellman parameters and the public key may be chosen new for every session, we call it as ephemeral Diffie-Hellman key exchange. Now the certificate does not have inbuilt Diffie-Hellman key parameters. But every time the server wants to communicate with the client, it will choose explicitly the Diffie-Hellman key parameters and then sign it and send to the client. Hence, this variant is referred as ephemeral Diffie-Hellman key exchange. Now, we come to the end of key exchange methods, wherein we started our discussion with how a certificate is shared by the server to the client in step 2 of the uh, handshake protocol. Now what happens over there is that the server sends its certificate and the client retrieves the public key contained in the certificate and uses that public key to encrypt the pre-master secret. Further to the discussion, we have seen that what happens if this certificate sent by the server is signature only certificate. Now if it is a signature only certificate, then the server will generate a temporary public private key pair. Now after selecting a temporary public key pair, the public key and the modulus are signed by the server using the private key of the server. Now this signed certificate is a public key and the certificate are sent by the server to the client. The client, upon receiving it, will verify the signature and then use it to encrypt the pre-master secret. Now subsequent to this discussion, we have discussed about the various key exchange methods available. Now either the client can prefer to use an RSA method or a Diffie-Hellman method. Now let's assume if the client uses a Diffie-Hellman method. In that case, there are two possibilities. One possibility is the fixed Diffie-Hellman key exchange method and the other one is ephemeral Diffie-Hellman key exchange method. Now what happens in case of fixed Diffie-Hellman key exchange method is that the signature itself contains the Diffie-Hellman key parameters, that is the prime number, the generator, the public key are all present in the signature and the signature is exchanged with that of the client. But the other counterpart of this fixed Diffie-Hellman key exchange is the ephemeral Diffie-Hellman key exchange method, wherein the certificate does not have the Diffie-Hellman key parameters. Now when does this situation occur? If the certificate is a signature only certificate, in that case there is absence of Diffie-Hellman key parameters. Now how do we achieve this Diffie-Hellman key exchange if there is absence of Diffie-Hellman key parameters? Now in that case, the server selects prime number P, G the generator, and then compute the public key G raised to a using G raised to a mod P by selecting its private key. And once all these are once this step is performed, all these parameters are signed. The signed parameters along with the public key and the signature are then sent to the client and further process of Diffie-Hellman key realization is used. Now this is about key exchange methods. Further to this discussion, we will there are other issues involved in SSL handshake protocol. The next issue that we will be discussing is server authentication. Now why do we need this server authentication? Now important credentials or important information is shared between the client and the server. The client should be able to verify the genuinity of the server. Now in the handshake protocol, we have seen that the first three methods, it is simple clear exchange simple exchange of messages in clear. That is nothing much is done, no encryption or anything is done over there. Now what is being done in case of server authentication is we need to verify the authenticity of the server which is communicating with the client. This authentication of the server is done in step 4 of SSL handshake protocol. Now what exactly happens over here? Let us see. Now in the SSL handshake protocol, we have seen in step 1, step 2 and step 3, lot of messages are exchanged as an handshake messages. Now, for all these handshake messages, a hash is computed by both the communicating parties, that is the client and the server. Now, this hash will act as integrity check for the previous messages that are exchanged. Now, once this hash is computed by the communicating parties, they are sent to each other in step 4. Now, the question that arises in our mind is, why is it that we are performing this hashing and integrity check? Now, all the handshakes that are used in the previous steps from 1 to 3, they are all handshake messages, they are all sent in clear between the client and the server, except for the encryption over the pre-master secret. Hence, since these messages are sent in clear, it is possible for an attacker to modify these messages and create disruption to the session establishment. Now, moving further, now let's take a simple example as to what happens if the attacker is able to modify the messages and how we can combat these particular modifications or attacks. Now, for example, let's say an attacker during the negotiation of the cipher suite changes the choice of 128-bit DES key with a 56-bit key. Obviously, if we are using 128-bit DES key, the strength of the cipher will be very high. But what the attacker has done is, he has modified it to 56-bit DES key. In this case, when we use this particular key to encrypt the plain text or the message, it generates a weaker cipher or a less strong cipher. Now, this weak cipher can be easily compromised by attackers. Now, this modification which is done by the attacker should not be possible or should not go undetected. Now, the calculation of MAC in the step 4 helps us detect any modifications over the handshake messages which are performed previously. Now let's see further. The keyed hash computed by the server is verified by the client. Now the client uses the server's MAC secret to verify the keyed hash. Now the server's MAC secret is one of the 6 derived secrets calculated in step 3. Now this secret is a function of the master secret. Now we know that the derived secret is obviously obtained from the master secret along with the nonces and also the predefined constants. Now this master secret in turn is a function of pre-mastered secret. Now finally we get to know that the MAC secret is obtained from one of the 6 derived secrets. Now all these secrets are performed and derived in step 3. Now this derived secret is obtained from master secret by applying a function. Now this master secret is in turn obtained from pre-master secret by applying a hash function over it. Now this is how we get the server and the client to verify their MAC secrets. Now let's recall that the pre-master secret is chosen by the client. Now it is encrypted with server's public key. Hence, only server alone can read it, because the server is the only person who can decrypt it using his own private key. and only the client and the server are aware of the 6 derived secrets or 6 derived computations. Now, the server, the client, only after receiving and verifying the keyed hash which is received from the server, it gets convinced, the client gets convinced and says that the server is finally authentic. Hence, authentication of the server is proved in the 4th step of SSL handshake protocol. Now, once the server is authenticated, now we move on to understanding what we mean by sessions and connections. Now, in the sessions and the connections, we'll try to differentiate between the session and the connection. If the session is long lasting, if it lasts for a long duration, in that case, a good practice would be to change the keys. We cannot use the same set of keys for a long duration. Now, SSL provides with 2 provisions. One provision is changing the keys by creating new connection within an existing session. We keep the same, we have the same session. Within this session, we create a new connection. Now, the advantage of using this method is the overhead of creating a new session is overcome. This will involve decryption of the pre-master secret with private key operation. Now, what is the second provision? The second provision provided by SSL is creation of new connection or creating a new connection. Over here, the pre-master secret is not chosen again. A new master secret is computed from the existing pre-master secret. So we have the pre-master secret and we will further derive a new master secret out of this pre-master secret. Along with that, 2 fresh nonces are selected, one each by server and the client. Now let's see the experiments performed by Apostopoulos. Now this scientist measured the overhead incurred by Apache web server with SSLE 8.0. The time taken to set up a new connection in an existing session just took 3 milliseconds. Whereas the overhead of setting up a new connection on a server using 1024-bit RSA keys is 45 milliseconds. Obviously, we can understand that using or establishing a new connection within an existing session will be more beneficial and less lightweight than that of setting up an entire new session over a server. This one will give us more overhead, and the setting up of a new connection in existing session will give us less overhead. Now let us conclude this particular topic by differentiating between the session state and state of a connection. Now the session state includes pre-master secret and the negotiated cipher suit and a session ID, whereas state of a connection will include 2 nonces, master secret, the 6 derived secrets, and the 2 message sequence numbers, one for each direction of the message transfer. So, having understood the differences between the session state and also the state of a connection, we can now move towards understanding the SSL record layer protocol. The secure socket layers record layer protocol is responsible for transmitting data securely using negotiated cipher suite of the step 1 and also the keys derived during the SSL handshake. Now, the main tasks of this record layer protocol include computation of MAC and and encryption computation. This is performed for every message, and also fragmentation is carried out if the data transmitted is very large. Now, if the data transmitted is large, then fragmentation occurs, and each fragmentation is less than or equal to 16 KB. Now let's see what happens when a connection is established. On establishment of a connection, the sequence counter is initialized on both the ends. Sequence counter keeps incrementing for each packet that is exchanged between the client and the server. The sequence number is not sent, but it is used during the computation of MAC. Now the sequence number is not sent along with the packet, but we use it for the computation of the MAC at both sender and also for verification of MAC at the receiving end. The MAC is computed on concatenation of 64-bit sequence and fragment. The next step is, what if the size of the data fragment is not a multiple of block size? Now obviously when it is not a multiple of the block size that is required, in that case we append bits to the data fragment so that it becomes a multiple of the block size. Now this appending of bits, we call it as padding. Now the data fragment along with the MAC and the pad, if required it is appended, is encrypted. Now after encryption is performed, a header is prepended to this particular encrypted data. So what is done is, initially we perform fragmentation if required. Now if this fragmented data is not a multiple of the block size, in that case we perform padding, that is adding extra bits to make the data fragment a multiple of the block size. Now the actual data fragment along with the MAC that is calculated and the padding, if it is done, totally they are encrypted. Now after encryption is performed, now this entire encrypted data is prepended with a header. That is, a header is attached in the front of this encrypted data. Once the header is prepended to the encrypted data, it is sent to the TCP layer, that is the underlying layer, for further processing. Now remember that the SSL record layer is below the handshake layer, and above the handshake layer is the application layer. Now once this packet is sent to the TCP layer for further processing, let's see the entire explanation with the help of a diagram. We have a fragment. Over this fragment a MAC is calculated. Once this MAC is calculated over this data fragment, we append this MAC at the end of the fragment. Now once this fragment is appended with the MAC, we will see if it is a multiple of the data block. Now if it is not a multiple, what do? We perform padding. Now over here padding is not depicted. Now once the padding is performed, the fragment along with the MAC and padding, if it is appended, all three together are encrypted. Once encryption is performed, now what is done is, a header is prepended to this encrypted block of fragment. Now this header, we call it as SSL record layer header. After appending, this packet is sent to TCP layer for further processing. Now the question that arises is, what does the header have? The header contains one byte which specifies the type of the content or content type field. This identifies the higher layer protocol that is used to process the fragment. So the content type field helps in identifying the higher layer protocol that is used to process the fragment. Now 2 bytes of data are used to specify the version number field. Finally, we have another field which specifies the length of the fragment in bytes. Now these are the 3 fields which are present in the SSL record layer header, protocol header. Now moving further with our discussion, now let's have a recap of what we have discussed in SSL record layer protocol. In the SSL record layer protocol, we started our discussion with the need for SSL record layer protocol. We need this SSL record layer protocol to securely transmit data between the client and the server. Now the main tasks are computation of MAC, encryption and fragmentation if required, if the data transmitted is very huge. Once that is done, we have discussed about what happens when a connection is established. We have sequence counter which keeps incrementing as and when the message is sent. But this sequence counter is not a part of computation of MAC or verification. It is not a part of the message itself, but it is used for computation and verification of MAC. Now further to this, we have seen now how this MAC encryption occurs and how it is further sent to TCP layer. Now the data fragment over for that we calculate the MAC. Now if the data fragment is not of appropriate size, then we perform padding to make it to the size of which will be a multiple of the block size. Now the data fragment along with the MAC and padding is encrypted, and to this encrypted data fragment we attach or prepend a SSL record layer header. This SSL record layer header has 3 fields. Now what are those fields? One is the content type field which will identify the higher layer protocol that is used to process the fragment, and the second one is the version number field which is of 2 bytes, and the third one is the field length that is length field which will specify the fragment size in bytes. The size of the fragment is usually 16 KB. Now moving on to OpenSSL, let's see what we mean by OpenSSL. OpenSSL is an open source implementation of the secure socket layer. It is based on SSL Lee library. Now this OpenSSL was developed by Eric and Hudson. Now what does this OpenSSL contain? What is this OpenSSL open source implementation? It has many libraries. Now these libraries help us with cryptographic algorithm implementation and digital certificate generation and validation. Now what is the use of having OpenSSL? Now with OpenSSL, it is easy for a developer to develop an application because there are a lot of APIs that are available. Now these APIs allow SSL enabled communication, that is a secure communication, and then easy setup of connection and easy concluding or tearing of the connection, and also helps in certificate storage and management and verification of certificates. Now with OpenSSL, a developer can rely and easily implement an application with required security. Now having come to the end of the session, now in this entire today's session we have discussed about the various key design ideas. We have understood what we mean by SSL record layer protocol, and also we have understood the concept of OpenSSL. Now this OpenSSL is nothing but an open source software implementation of our secure socket layer protocol. Now this protocol implementation has huge number of libraries and APIs which help in easy implementation of cryptographic algorithms and digital certificates generation and validation. Now, this OpenSSL helps developers uh, implement secure applications with ease. Having understood security at transport layer, we conclude this session. And if there are any queries, you can email me over this ID, or you can contact me over this particular number. Thank you. Have a good day.